Hello, Tech World. This is Tech Thoughts. In this three-part video series, I'll be exploring the topic of subnetting. When you've completed all three videos, you'll have an understanding of what subnetting is for, and you'll be able to properly calculate subnets. This is the second video in the series where I'm going to be exploring the properties of an IP address and IP classes. If you haven't yet seen video 1 on binary conversion, I highly recommend you check it out first. I've linked it in the comments below. If you're already comfortable with binary conversion, then let's go ahead and get started.
So in this video, we'll be discussing what makes an IP an IP. So we know an IP address. We'll write up a typical one here, 192.168.1.1, a typical Class C address. So let's discuss how does this relate to binary, and why is binary important? Why do you have to know that in order to understand IP addressing and subnetting? Well, basically, we can break this IP address down into 4 sections. There's actually 4 sections here, and that could be written out like this. So we have something dot something dot something dot something. In this case, 192.168.1.1. Each of these in an IP address can be a range of 0 to 255 in each section. So I can have a possibility of 0 to 255. Now, we learned in our last lesson the maximum number we can make in an 8-bit system is 255. And it's no coincidence that that is the case here. So each of these different sections is 8-bit. We can't, of course, prove this because 2 to the 8th is 256. And this is a range of 0, which counts, to 255. So it's a total of 256 numbers to choose from. So each of these is 8-bit, and it's no coincidence that we call each of these sections an octet. And so all of these together are referred to as octets. And what we basically have here is the ability for 8 different binary bits. So using binary conversion, we can actually write this IP address, 192.168.1.1, as 11, and then 168 will binary out to 1, 0, 1, 0, 1, 0, 0, 0. 1, of course, will be 7 zeros and a 1, and of course this one will be the same. So each of these is 8 bits for a maximum range of 0 to 255. Now, we don't just have an IP address, we of course also have a subnet mask. So you may be given a IP address of 192.168.1.1, and this is a Class C address. So it will have a subnet mask typically of 255.255.255.0. These 255s should come as no surprise. This is the maximum number, and we know from our binary conversion that in order to make this number, that all 8 bits must be turned on. So my subnet mask here will look like this. All 8 bits turned on, which adds up to 255. Again, all 8 bits turned on. And the same here. Both 255. And my last one is 0, which of course makes all of these bits 0. So what you end up with is these three octets are all turned on. So these are all turned on with ones. And this octet, this last one here, is turned off. A subnet mask is essentially telling you what belongs to the network and what belongs to the host. So we can say that all of these here can be written this way. Since we have 8 bits turned on, all 8 of these belong to the network. All of these belong to the network as well, in addition to this one. But none of these are turned on. So these belong to the hosts. So in this example, in the Class C subnet mask, we have 3 octets that belong to the network. These belong to the network. We have 1 octet here that belongs to the host. In essence, what I've done here by dividing certain bits into network and certain bits into hosts is I've locked out part of this IP address. In this example, in the 192.168.1.1 example, because the first 3 octets belong to the network, this is locked in. Because all the bits remaining belong to the host in this 0 octet, this right here has a range of 0 to 255. And let me give you an example of how this operates. So here we have an example of 192.168.1.1. Again, these 3 octets belong to the network. So if we had another IP address on a different computer with this, and say 1.2, these 2 IP addresses based on their mutual subnet mask of 255.255.255.0 can both communicate because they belong to the same network. Now, using the same example, 192.168.1.1, if I were, for example, to take 192.168.2.2, remember, because of the subnet mask and these bits being turned on and belonging to the network, this is locked in, and this has a range of 0 to 255. Because this is not the same, these are different networks. They cannot communicate with one another without the use of a router. So these 2 networks are essentially separated because of their subnet mask. They do not belong to the same subnet. Because again, because all of these were turned on and belong to the network, this .1 here and this .2 here are 2 totally and independent networks. Now remember, because we have this 0 here, and we have a range because of that, because we have all of these host bits to work with now, we have a full range of 0 to 255. 192.168.1.1 and 192.168.1.50 are still both within the range of 0 to 255. Because their subnet mask locks in this right here, these are the same network. They are within the same range. And so these 2 IP addresses here will be able to talk to each other without the use of a router. We have a working range of 0 to 255 for all octets, but we typically divide that range into different classes and assign different subnet masks based on those classes. This is not always set in stone, but it is a general practice in the networking community. So we'll start off with class A. And although we do have that 0 to 125, a class A is going to be divided from 1 to 126, which you see here. And it typically carries a subnet mask of 255.0.0.0. This can be, of course, written in binary. And based on your binary skills you've learned so far, you know that all 8 of these bits will be turned on. And of course, no bits will be turned on here, no bits will be turned on here, and no bits will be turned on here. You could have, of course, write out all 8 zeros, but for shortcut, I've just done this. You know, because these are turned on, that they are written as the network. So this octet right here belongs to the network. These will all be written as hosts. So all of this belongs to the hosts. So what we have here is very few networks, but very many hosts. And we can see that here. The total number of networks is only 126, whereas the total number of hosts is 16,777,214. So you might ask yourself, where do we get this 2 to the 24 number? Well, remember, there are 8 bits here, 8 bits here, and 8 bits here, and 8 times 8 times 8 is 24. And you might be asking yourself, well, then why, if I have 8 bits here, do I not see 2 to the 8th here? And notice that we go in class A from 1 to 126, but we leave out 127. 127, full range, 0.0.0, all the way to 127.255.255.255 is considered a private range and is reserved. So we give up 1 bit in the class A, giving us only 126 to work with. So this is where we get this network host 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 in this column here. Because of that 255, that first bit being filled in, all 8 bits turned on, this does belong to the network, and all 3 of these, because that is 0 and no bits are turned on, all belong to the host. So now let's take a look at class B. And class B is typically written with a subnet mask of 255.255.0.0. And you should be very comfortable writing this in binary at this point. And because this is 255, we know that all 8 bits are turned on, as well as here. And of course, nothing being turned on here, and nothing here as well. This is re-emphasized in the chart because the first 2 will belong to the network, and the second will belong to the hosts. So these octets belong to network, and these octets belong to our hosts. So because we have 8 here and 8 here, 8 bits to work with, this is where we get this 2 to the 16th from. And you might also be asking, well, I have 8 and 8 here. Why do I not have 2 to the 16th here? Well, although it is not emphasized on this graph, the ranges of 169 dot and the range of 172 dot are both reserved for private addressing. So we give up 2 bits for that. So we only have 2 to the 14th to work with. Now, to give you an example of a class B, because both of these first 2 octets belong to the network, if I were to use, for example, 129.5.4.200 and 129.5.8. 100. Both of these first two are the same, and they belong to the same network. They will be able to communicate. 129.5.4.200 and 129.6.4.201 do not belong to the same network because of the subnet mask. These are differing and will require a router to communicate as they have been separated and subnetted out. Notice in Class B that we have a closer range of how many networks there can be versus how many hosts on each of those networks that you have available. We'll now talk about Class C, which is a range of 192 to 223 and typically represented by a 255.255.255.0. Again, binary representation. And I'll go ahead and fast forward a little bit. So all of these belong to the network. This belongs to the hosts. And notice that we have a great many networks here, but not very many hosts. So each one of these networks, let's say 192.168.1, will only have an available 0 to 255 hosts to work with. So you can't have a great many networks in Class C, but not very many hosts on each one of those networks. Class D and E are a little specialized, so we won't be talking about those too much. But lastly, I would like to talk about, you may find this chart a little bit difficult to memorize. I'll show you a quick shortcut that should make it a little bit easier. You may find it a little bit challenging to memorize which of these IPs falls into which range. So I'll show you a quick little shortcut using the table of twos on how to memorize which of the IPs goes into which range. So it goes without saying that from our first lesson that you kind of have to memorize the table of twos up into 7. And that's pretty easy to do because it just doubles each time, 1, 2, 4, 8, 16, 32, 64, and 128. The classes can seem a little bit more confusing, and I'll show you how it actually isn't. So we know that we're going to start our classes with 1. And rather than going left to right, I want you to think about going down. And we're going to think about going across. So notice that my first number in the table of twos is 128. So we'll go ahead and write, we know we start with 1. We're going to write 128. Now 128 plus 64 equals 192 here. And 192 plus 32, so we're at 192 right now, plus 32 equals 224. So now we're at 224 plus 16 equals 240. So using the table of twos, you've basically written out your ranges, and you just have a few things to remember, which is that we ignore 127, so you know this will go to 126. You know this will go to 191. 192 will go to 223. And 224 will go to 239. And just remember that although we usually go to 255, your Class C will stop just short of that at 254. So this is an easy way to memorize these. And you will have to know that Class A, of course, is going to be taking up 255, Class B, 255, 255, and then Class C, 255.255.255.0, which is a little easier to remember. And based on your binary skills, you should be able to figure out this portion right here relatively easier. So I hope part 2 has been helpful in dissecting what an IP is and how it relates to binary, and why understanding binary conversion is very important for IPs, and how these classes break down and separate IP addresses into different networks based on that subnet mask.
If this video was able to help you out, go ahead and click that like button and subscribe for more Tech Thoughts videos.